There is a region of space approximately 26,000 light years from where you are sitting, at the center of the Milky Way, where the laws of physics break down, where matter is compressed to infinite density, where time stops, where light itself cannot escape. We have photographed it. We have measured its mass. We have detected the gravitational waves from two of them colliding. We have watched stars orbit it at a fraction of the speed of light, and we do not fully understand it. We have been studying black holes for over a century, and the deeper we look, the stranger they become. This is the complete guide, everything physics knows. And honestly, everything it does not, there will be no shortcuts here. No comfortable simplifications. We are going all the way in. And that means starting at the very beginning with what a black hole actually is, and building from there to the frontier where the smartest people in physics are genuinely uncertain and genuinely arguing. Let us begin. A black hole is a region of space-time where gravity is so extreme that nothing, not matter, not radiation, not light itself, can escape once it has crossed a boundary called the event horizon. That is the technical definition. And while it is accurate, it is not satisfying because it raises immediately the question of what gravity actually is and what space-time actually is and what it means for nothing to escape. So let us build this from the ground up. Gravity in Newton's physics was a force, an attractive pull between masses, acting instantaneously across any distance. Newton himself was deeply uncomfortable with this. He knew that action at a distance with no mediating mechanism was philosophically troubling. But the mathematics worked extraordinarily well. For 2 centuries, Newton's gravity explained the motion of every planet, every moon, every comet, every tide with extraordinary precision. And then came Einstein, and everything changed. And in Einstein's general relativity, gravity is not a force. It is geometry. It is the curvature of space-time itself. Mass and energy curve the space-time around them. And other masses moving through that curved space-time follow paths called geodesics that look like they are being pulled by a force. But they are simply following the straightest possible path through curved space. The Earth does not attract the moon. The Earth curves the space-time around it. And the moon follows the straightest path through that curved space-time, which happens to be in orbit. This is a profound reframing, not just a different description of the same phenomenon, a fundamentally different understanding of what space, time, matter, and gravity actually are. And it has a consequence that Newton's gravity did not have in general relativity. If enough mass is concentrated in a small enough region, the curvature of space-time becomes so extreme that geodesics, the paths that light and matter follow, begin to curve back on themselves at a certain threshold. ALL geodesics within a certain radius point inward. There are no outward-pointing geodesics. Light trying to travel outward finds itself on a geodesic that curves inexorably inward. It cannot escape, not because something is blocking it, but because space-time itself is curved so severely that outward is no longer a direction that exists inside the event horizon. This is the event horizon, the boundary of a black hole, the point of no return, not a physical surface, not a wall. Nothing marks it in space. If you fell through the event horizon, you would feel nothing special at the moment of crossing. There is no barrier, no surface, no signal, just a mathematical threshold beyond which escape is impossible. And from outside, from a safe distance, you could never see anyone cross it. Because light from near the horizon is so severely gravitationally redshifted and so severely time dilated that from your perspective, the person falling in appears to slow down, freeze, never quite reach the horizon, fade to deep red, and eventually become too faint to detect. Inside the infaller's perspective, they cross in finite time. They feel nothing special at the crossing. And then they fall toward the singularity, where things get very strange, but we will come back to that. First, let us understand where black holes come from. How does a region of space develop this extreme geometry? There are several mechanisms, but the most important, the one responsible for the majority of black holes we observe, is stellar collapse. The life of a star is a constant battle between two forces, gravity, which tries to compress the star inward, and radiation pressure from nuclear fusion in the core, which pushes outward. For most of a star's life, these two forces are in balance. The star sits in hydrostatic equilibrium, stable, burning, shining, but this balance depends on fuel, and fuel runs out. A star begins its life fusing hydrogen to helium in its core. This provides the outward pressure to resist gravity. When the hydrogen is exhausted, the core contracts, temperatures rise, helium ignites, fusing to carbon and oxygen. Then the helium runs out. And for massive stars, stars with masses above roughly 8 times the mass of our sun, the process continues. Carbon fuses to neon and magnesium, then oxygen, then silicon. Each stage provides temporary support. Each stage is faster than the last. Hydrogen burning takes millions of years. Silicon burning takes about a day, and silicon burning produces iron, and iron is where the nuclear ladder ends. Iron is the most tightly bound nucleus, the most energetically stable. It does not release energy when fused. It absorbs energy. So when the iron core of a massive star reaches the Chandrasekhar limit, about 1/4 solar masses, nuclear fusion stops providing support. And gravity wins catastrophically in less than a second. The iron core collapses from the size of Earth to the size of a city, roughly 20 kilometers, in milliseconds. The collapse is so rapid and so violent that the rebounding shockwave blows the outer layers of the star apart in a supernova explosion. One of the most energetic events in the observable universe, briefly outshining its entire host galaxy. The core that remains, if the progenitor star was massive enough, collapses past the point where even neutron degeneracy pressure can support it, and becomes a black hole, stellar mass black hole, typically between 3 and 100 solar masses. But stellar collapse is not the only way to make a black hole. There are at least 4 categories. Stellar mass black holes formed from stellar collapse range from about 3 to a few tens of solar masses, the kind we detected with LIGO, the kind whose event horizons are tens of kilometers across. Intermediate mass black holes ranging from hundreds to hundreds of thousands of solar masses. Evidence for these has been found, but they remain less well understood. Their formation mechanism is debated, possibly mergers of stellar mass black holes, possibly collapse of massive gas clouds in the early universe, supermassive black holes from millions to tens of billions of solar masses, found at the centers of virtually all large galaxies, including ours. Sagittarius A, at the center of the Milky Way, approximately 1 million solar masses. M87 in the Virgo cluster, approximately 5 billion solar masses. How supermassive black holes formed is one of the great open questions in astrophysics. They appear to have been in place very early, within a billion years of the Big Bang. Growing fast, their formation is not well understood, and primordial black holes, a hypothetical 4th category, possibly formed in the extreme density fluctuations of the very early universe, before any stars existed. These could range from tiny, less than a gram, to very large. None has been definitively detected, but they remain a serious theoretical possibility. And depending on their mass, they might have already evaporated via Hawking radiation, or might still be around as candidates for dark matter, or as sources of gravitational wave signals. Now, let us talk about the structure of a black hole. What does one actually look like, not to the eye, which cannot see one, but in terms of its geometry? A non-rotating, uncharged black hole is described by the Schwarzschild solution to Einstein's field equations. Derived by Carl Schwarzschild in 1916, just weeks after Einstein published general relativity, while Schwarzschild was serving in the German army on the Russian front during World War I. He died months later, but his solution survived. And it is the foundation of our understanding. The Schwarzschild solution describes a spacetime with perfect spherical symmetry. One parameter, mass m, and a critical radius, the Schwarzschild radius. The Schwarzschild radius is r is equals 2gm divided by c squared, where g is the gravitational constant, m is the mass, and c is the speed of light for the sun, approximately 3 kilometers, for Earth, approximately 9 millimeters. If you could compress the Earth to the size of a marble, it would become a black hole. If you could compress the sun to the size of a small city district, it would become a black hole. For Sagittarius A, approximately 12 or million kilometers, larger than the orbit of Mercury. For M87, approximately 19 billion kilometers, larger than our entire solar system. The Schwarzschild radius defines the event horizon for a non-rotating black hole at this boundary. The escape velocity equals the speed of light, and the curvature of space-time becomes so extreme that the future, all possible futures, points toward the singularity at the center. Real black holes almost certainly rotate, because the stars that form them rotate, and conservation of angular momentum means that as the star collapses, as its radius decreases by a factor of 10,000 or more, its rotation rate increases dramatically. The way a spinning ice skater speeds up when they pull in their arms, multiplied by many orders of magnitude. A rotating black hole is described not by the Schwarzschild solution, but by the Kerr solution, derived by Roy Kerr in 1963. The Kerr black hole has 2 important surfaces rather than one. The outer boundary is the static limit, also called the ergosphere boundary. Within this boundary, space-time itself rotates, dragged around by the spinning black hole, and nothing can remain stationary, not even light. Everything must rotate in the same direction as the black hole. This is called frame dragging. And it has been measured in experiments near Earth, where the effect is tiny, confirming general relativity. Between the static limit and the event horizon is a region called the ergosphere, where spacetime is dragged so fast that nothing can remain stationary, but objects can still escape. The true event horizon of a Kerr black hole is inside the ergosphere, and the ergosphere is the site of a remarkable process called the Penrose process. In the ergosphere, spacetime is dragged at superluminal rates. An object entering the ergosphere can split into two pieces. One piece falls into the black hole with negative energy, as defined by an outside observer. The other piece escapes to infinity with more energy than the original object had. Where did the extra energy come from? The rotation of the black hole. The escaping fragment carries away angular momentum and energy extracted from the spinning spacetime itself. The Penrose process can extract up to approximately 29% of the mass energy of a maximally rotating black hole. This is one of the most efficient energy extraction mechanisms in the universe, and it may be the power source behind some of the most energetic phenomena we observe, including quasars and relativistic jets. Now, let us go inside, past the event horizon, and ask what is in there. This is where physics becomes genuinely strange, and where our theories begin to strain. The Schwarzschild solution predicts that at the center of the black hole, at radius 0, is a singularity, a point where the density becomes infinite. The curvature of space-time becomes infinite. The tidal forces become infinite. Everything becomes infinite. And here is the first honest statement about singularities. They are almost certainly not real. In physics, when a calculation produces infinity as an answer, it is almost always a signal that the theory has been pushed beyond its domain of validity, that the mathematics has broken down, that we are using the wrong theory. The singularity predicted by general relativity inside black holes is almost certainly a signal that general relativity fails at extremely short distances, at extremely high densities, where quantum mechanics must be taken into account. We do not have a working theory of quantum gravity. That theory, whatever it turns out to be, will likely replace the singularity with something finite, something physical, some structure at the Planck scale, but we do not know what. So when we say there is a singularity at the center of a black hole, what we mean is something is there, something extreme, something our current physics cannot describe. And whatever it is hidden behind the event horizon, invisible to the outside universe. This invisibility of the singularity is a deep principle in general relativity called cosmic censorship, proposed by Roger Penrose in 1969. The cosmic censorship conjecture says that singularities, wherever they form, will always be hidden behind an event horizon. A naked singularity, one visible to the outside universe, would be catastrophically bad for predictability. It would be a point from which arbitrary amounts of energy and information could emerge, with no way to predict what, destroying the causal structure of spacetime. Penrose conjectured this cannot happen. General relativity will always form an event horizon to clothe its singularities. But this has never been proved. And there are mathematical solutions to Einstein's equations, highly idealized ones, that do produce naked singularities. Whether physical processes can create them remains an open question. Let us now talk about what happens to someone who falls into a black hole. There are two very different stories depending on where the black hole is and how big it is. For a small black hole, stellar mass, the tidal forces outside the event horizon are extreme. Tidal forces arise because gravity falls off with distance. If you are falling toward a black hole feet first, gravity is stronger at your feet than at your head. The difference in gravitational pull tries to stretch you along the direction of fall. And simultaneously, gravity is stronger at the near side of your body than the far side. And the far side is pulled toward the center, converging, so you are stretched in one direction and squeezed in the other simultaneously. This process is called spaghettification, and for a stellar mass black hole, it begins well outside the event horizon. You would be stretched and compressed to death before reaching the event horizon, spaghettified, reduced to a stream of particles flowing into the singularity, long before crossing the boundary of no return. But for a supermassive black hole, the event horizon radius is so large that tidal forces at the event horizon are actually quite mild. You could cross the event horizon of M87, which is larger than our solar system, without feeling any special distress at the moment of crossing. The curvature of spacetime at the event horizon of a 6 billion solar mass black hole is actually less extreme per unit distance than near a stellar mass black hole, because the Schwarzschild radius grows linearly with mass, but tidal forces fall off as the cube of the distance. So at the horizon of a supermassive black hole, tidal forces are much smaller than at the horizon of a small one. You fall through the event horizon feeling nothing special. Locally, space still looks normal. Physics still works normally. You can still do experiments, talk to companions who fell in with you, read a book for a while. But you cannot send a message out. No signal you emit will reach the outside universe. You are causally disconnected from everything outside the horizon. And then, as you fall toward the singularity, tidal forces grow, space-time curvature grows, things get strange, and eventually, something happens at the singularity. We do not know what. We genuinely do not know. That is the honest answer. From outside the black hole, time near the event horizon runs very slowly relative to time far away, gravitational time dilation. A clock at rest near the event horizon, if such a thing could exist, would tick almost infinitely slowly as measured by a distant observer. Light emitted from near the horizon is gravitationally redshifted, shifted to longer wavelengths, losing energy as it climbs out of the gravitational well. At the event horizon, the redshift is infinite, time stops, light has zero energy, which is why nothing escapes. If an astronaut falls toward a black hole, their distant colleague sees them slow down, redden, dim, and asymptotically approach the horizon but never quite reach it. From the outside, they appear frozen at the horizon forever, becoming infinitely redshifted, fading from view. Now, let us talk about one of the most profound discoveries of 20th century physics, Hawking radiation. In 1974, Stephen Hawking combined general relativity and quantum field theory in a semi-classical calculation. Not a full theory of quantum gravity, just quantum fields on a curved space-time background. And he found something extraordinary. Black holes are not black, they radiate. The quantum mechanical vacuum is not empty. It is filled with quantum fluctuations, virtual particle-antiparticle pairs continuously popping into existence and annihilating each other. These are not real particles, they are fluctuations of the quantum field. And normally they have no lasting effect. They appear and disappear. Net contribution, zero. But near the event horizon of a black hole, something different can happen. A virtual pair forms near the horizon. One particle falls inside the horizon. The other escapes to infinity. The one that escapes is real. It has positive energy and carries that energy away. The one that falls in has negative energy as seen by a distant observer and reduces the mass of the black hole. The black hole loses mass. And to the distant observer, the escaping particle looks like thermal radiation emitted by the black hole with a temperature Th equals c cubed divided by eta g mkb. The Hawking temperature is inversely proportional to mass. A small black hole is hotter and radiates more intensely. A large black hole, a stellar mass black hole, has a Hawking temperature of approximately 60 nanokelvin, 0.00006 Kelvin, far below the cosmic microwave background temperature of 7 Kelvin. So large black holes are not actually evaporating in any meaningful sense. They absorb radiation from the CMB faster than they emit Hawking radiation. But in the distant future, after the universe has cooled below the Hawking temperature of the last remaining black holes, they will evaporate. As we discussed in the Universe End video over incomprehensibly long timescales, Hawking radiation was one of the most important results in theoretical physics of the 20th century because it connected three seemingly unrelated things: gravity through the black hole, thermodynamics through the temperature and entropy, and quantum mechanics through the particle production mechanism. And this connection led immediately to one of the deepest unsolved problems in all of physics, the information paradox. Before Hawking radiation, information seemed safe around black holes. Things could fall in, but the black hole was eternal. The information was forever hidden but not destroyed. After Hawking, the black hole evaporates, eventually, completely. It radiates away all its mass as thermal radiation. And thermal radiation is featureless, random. It carries no information about what fell in. If a book falls into a black hole, and the black hole evaporates into featureless thermal radiation, where is the information that was in the book? In quantum mechanics, information cannot be destroyed. This is a fundamental principle, unitarity. The evolution of quantum states is always described by unitary transformations, transformations that preserve information. If you know the complete quantum state of a system at one time, you can, in principle, reconstruct the complete state at any other time, past or future. Information is conserved. Always. This principle underlies the consistency of quantum mechanics. If it fails, quantum mechanics breaks down. But Hawking's calculation suggested that information is destroyed in black holes, that the radiation carries no information about what fell in. Just a thermal spectrum determined only by temperature, which depends only on mass. This would be a violation of unitarity, a violation of the fundamental principles of quantum mechanics. Hawking himself accepted this conclusion. He believed information was destroyed and spent years defending this position. Most particle physicists believe the opposite, that somehow, in ways Hawking's semi-classical calculation could not capture, the radiation actually is encoded with information about what fell in, subtly, invisibly. But there, in tiny quantum correlations in the radiation, This argument between Hawking and the broader physics community became one of the defining intellectual disputes of late 20th and early 21st century physics. In 1997, Stephen Hawking and Kip Thorne made a bet with John Preskill. Hawking and Thorne, information is destroyed. Preskill, it is not. The bet was a baseball encyclopedia. In 2004, Hawking conceded. He declared that quantum effects he had not accounted for must encode information in the Hawking radiation. He gave Preskill the encyclopedia, though Preskill noted, in the spirit of the bet, that the information was still a bit scrambled, and Thorne never conceded. Kip Thorne did not believe the argument Hawking gave for conceding was sufficient. The debate was not over. It is not over. It is not over now. The problem deepened in 2012 with a result by Ahmed Almari, Donald Marolf, Joseph Polchinski, and James Sully, the AMPS paper that made the information paradox genuinely acute. The AMPS argument, the firewall argument, goes roughly like this. Three principles seemed unassailable. First, the equivalence principle. An infalling observer should see nothing special at the event horizon. Locally, physics should be normal. Second, unitarity. Information must be preserved. The radiation must be entangled with the information that fell in. Third, no drama for the infalling observer, equivalent to the equivalence principle restated. The problem, for information to be preserved, the late-time Hawking radiation must be entangled with the early-time radiation, with all the radiation that came before. But this entanglement budget is limited. Each particle can only be fully entangled with one thing. If the outgoing Hawking particle is entangled with the early radiation, as required for information preservation, it cannot also be entangled with its interior partner, as required for a smooth, normal event horizon. If the interior entanglement is broken, something dramatic happens at the event horizon. The broken entanglement corresponds to a wall of energy. An infalling observer would not cross a calm horizon feeling nothing. They would hit a wall of high energy radiation, a firewall, and be instantly incinerated. This is disturbing because the firewall seems to violate the equivalence principle, one of the foundational principles of general relativity. The AMPS paper was a bombshell. It forced physicists to choose violate unitarity, or violate the equivalence principle, or find a third option nobody had thought of yet. The paper sparked an enormous amount of work, new proposals, new ideas, none completely satisfying. One of the most intriguing proposals came from Juan Maldacena and Leonard Susskind in 2013. Their proposal, ER equals EPR, Einstein-Rosen bridges equal Einstein-Podolsky-Rosen correlations. In other words, wormholes equal entanglement. The Einstein-Rosen bridge is what Schwarzschild's solution contains if you extend it fully. Not just the black hole exterior, but a complete spacetime with two exterior regions, two black holes, connected by a bridge. The ER bridge, a wormhole. The Einstein-Podolsky-Rosen correlations are quantum entanglement, the spooky action at a distance that Einstein famously found disturbing. Maldacena and Susskind proposed. These are the same thing. Quantum entanglement between two systems is a wormhole connecting them. Maximally entangled systems are connected by a short wormhole. Less entangled systems, a longer wormhole. No entanglement, no wormhole. If ER equals EPR is correct, then when an infalling particle is entangled with the outgoing radiation, it is connected to that radiation by a wormhole, not just abstractly entangled. Physically connected through the geometry of space-time and the firewall. The energy wall that would form if the entanglement is broken would correspond to the wormhole being severed, which in this picture would be physically equivalent to a violent event, consistent with the firewall prediction, but avoiding the contradiction by providing a geometric picture of what entanglement actually is. ER equals EPR is not a proven theorem. It is a conjecture, but it is a deep and beautiful one. That suggests space-time geometry itself might be made of entanglement, that the connectivity of the universe, the existence of space between things, might be a consequence of quantum correlations. This is the frontier of physics, and it is genuinely uncertain and genuinely exciting. Now, let us talk about black hole thermodynamics, because Hawking's discovery did not come from nowhere. It was preceded by a remarkable set of results in the early 1970s by Jacob Bekenstein and others that established that black holes must have thermodynamic properties. The zeroth law of black hole mechanics. The surface gravity of a stationary black hole is constant over the event horizon. Analogous to the zeroth law of thermodynamics, the temperature of a system in equilibrium is constant throughout. The first law, a small change in the mass energy of a black hole is related to changes in its area, angular momentum, and charge. Analogous to the first law of thermodynamics, energy conservation. The second law, the crucial one, was discovered by Hawking himself in 1971. Before Hawking radiation, Hawking's area theorem, the total area of black hole event horizons can never decrease in any physical process. Two black holes merge. The area of the final black hole is at least the sum of the areas of the originals. This is analogous to the second law of thermodynamics. Entropy never decreases. Bekenstein proposed the analogy was not just mathematical, that black holes actually have entropy, proportional to the area of their event horizon, the Bekenstein-Hawking entropy, S equals A divided by 4 in Planck units. Where A is the area of the event horizon, this is one of the most important equations in theoretical physics. The Bekenstein-Hawking entropy of the Milky Way's central black hole, Sagittarius A, is approximately 10 to the 90 in natural units, a number larger than the total number of atoms in the observable universe, and it tells us something profound about the information content of the black hole. The entropy tells us how many bits of information are encoded in the black hole's structure. And the fact that it is proportional to area, not volume, is extraordinary in ordinary physics. The information content of a region scales with its volume. More space, more bits, but for black holes, the information scales with the surface area, not the volume. This is the holographic principle. The idea that in quantum gravity, the information about the interior of any region is fully encoded on its boundary surface, not in the interior, on the boundary, suggested by Gerard Hooft and Leonard Susskind, and dramatically supported by a specific realization, the AD-CFT correspondence, proposed by Juan Maldacena in 1997. And one of the most important theoretical results in physics of the past 30 years. The AD-CFT correspondence says that a theory of gravity in a certain type of space, anti-de Sitter space, is exactly equivalent to a quantum field theory without gravity living on the boundary of that space. Dimension lower without gravity, the two theories describe the same physics, in different languages, and crucially, the quantum field theory on the boundary is unitary. It preserves information, which implies the gravitational theory must also preserve information, which implies information is not destroyed in black holes. Hawking was wrong. But how the information escapes in a gravitational language, I still not fully understood. Now, let us talk about what we have actually seen, because this is not all theoretical. We have real images, real data, real detections. On April 10th, 2019, the Event Horizon Telescope collaboration published the first image of a black hole shadow. The target, M8765 5 billion solar masses, 55 million light-years away, in the galaxy Messier 87. The image shows a bright ring of emission, bent light from the accretion disk, surrounding a dark region, the shadow of the event horizon. The ring has a diameter consistent with the predicted Schwarzschild radius for a black hole of that mass. The asymmetry of the ring, one side brighter than the other, is consistent with the Doppler effect from the rotating accretion disk. Gas approaching us on one side appears brighter, gas receding appears dimmer. The image confirmed the existence of objects with the properties predicted for supermassive black holes. It was the first direct visual evidence. Then on May 12, 2022, the EHT published an image of Sagittarius A, the black hole at the center of our own galaxy, 1 million solar masses, 26,000 light-years away. Schwarzschild A is a much harder target than M87. The accretion disk material orbits much faster, in minutes rather than decades, meaning the image blurs as the source changes during the observation. The collaboration developed techniques to handle this variability and produced an image strikingly similar to M87. A bright ring surrounding a dark shadow, confirming that the object at the center of the Milky Way is indeed a supermassive black hole, consistent with all predictions of general relativity. And then there are gravitational waves. On September 14, 2015, the LIGO detector in Hanford, Washington, and Livingston, Louisiana simultaneously detected a gravitational wave signal, a ripple in the fabric of spacetime. The signal matched the predicted waveform for two black holes of approximately 29 and 36 solar masses spiraling toward each other and merging. The merger produced a black hole of approximately 62 solar masses, 3 solar masses worth of mass converted to gravitational wave energy in a fraction of a second. The peak power output, approximately 36 times 10 to the 49 watts, more than the combined light output of all stars in the observable universe at the moment of merger, for a fraction of a second. This detection, announced February 11, 2016, was one of the great scientific moments of the 21st century. It confirmed the existence of stellar mass black holes, confirmed that black holes merge, confirmed that merging black holes produce the gravitational waves predicted by general relativity. Measured the chirp, the rising frequency of the waves as the black hole spiraled in, exactly as predicted. and opened gravitational wave astronomy as a new observational window on the universe. Since then, LIGO and its partners have detected dozens of black hole mergers, giving us a census of stellar mass black holes, and surprising results, including black holes in the pair instability gap, masses that theory suggested were hard to produce through stellar evolution alone, and mergers between black holes of very different masses, raising new questions about how these systems formed. Let us talk about what lives near black holes. Because the region around a black hole is not empty. It is some of the most energetic real estate in the universe. For actively accreting black holes, ones with material falling in, a structure forms called an accretion disk. Gas spiraling informs a rotating disk, heats up as it spirals inward, losing gravitational potential energy. Temperatures in the inner regions of accretion disks around stellar mass black holes can reach tens of millions of degrees, emitting X-rays. These are the systems detected by X-ray astronomy satellites around supermassive black holes. The accretion disk can power some of the most energetic phenomena in the universe. A quasar is an actively accreting supermassive black hole, accreting at or near its maximum rate. Quasars can outshine their entire host galaxies by factors of hundreds or thousands. The most luminous quasars output more energy per second than 10 trillion suns. All of it ultimately powered by the gravitational potential energy released as matter falls toward the central black hole. The efficiency of this energy extraction, the fraction of infalling mass that is converted to radiation, is approximately 642%. Depending on the spin of the black hole, compare this to nuclear fusion, approximately 0.7% efficiency. Black holes are extraordinary engines. Many accreting black holes also produce relativistic jets, narrow beams of plasma accelerated to near the speed of light, and shot perpendicular to the accretion disk, extending in some cases for millions of light years. The jet from M87 extends for approximately 5,000 light years and was first photographed in 1918, a century before we imaged the black hole that powers it. The mechanism by which jets form is not fully understood, but likely involves the Blanford-Zenajec process, the extraction of rotational energy from a spinning black hole via magnetic field lines threading the event horizon. Around our own galaxy's central black hole, the situation is different. Schwarzschild is not actively accreting at anything like its maximum rate. It is relatively quiet, occasionally flaring in X-ray and infrared emission as clumps of gas fall in. This relative quiescence allowed the gravity collaboration to do something extraordinary. They tracked the orbits of individual stars, labeled S2, S38, and others, orbiting Schwarzschild at distances of hundreds to thousands of astronomical units. From these orbital measurements, the mass of Schwarzschild has been measured to extraordinary precision, 444 million solar masses. Within an accuracy of about 0%, the star S2 reaches a maximum speed of approximately 7% of the speed of light at closest approach, and its orbit shows the precession predicted by general relativity, confirming that the object at the center is consistent with a curved black hole. Now, let us talk about what we still do not know, because this is a central promise of this video, and there are profound open questions. We have discussed the information paradox and the firewall paradox, but there are others. The nature of the singularity. What actually exists at the center? This requires quantum gravity, which we do not have. The formation of supermassive black holes. How did 5 billion solar mass objects exist when the universe was less than 1 billion years old? The formation mechanism is not settled. The interior structure. What does the space-time look like inside the event horizon? For a rotating curved black hole, which all real black holes are, the interior is more complex. The inner horizon, the Cauchy horizon, is where predictability breaks down. It is a surface beyond which the future is not determined by the past. Classical general relativity breaks down, and what replaces it is unknown. There is also the question of black holes and quantum gravity. Every approach to quantum gravity makes predictions about black hole physics. Loop quantum gravity predicts the singularity is replaced by a Planck density quantum region. String theory predicts, through AdCFT, that information is preserved and provides a specific realization. The fuzzballs, objects that look like black holes from outside but have a stringy interior structure without a singularity or a sharp event horizon. In the fuzzball picture, the event horizon is not a region of nothing. It is a quantum mechanical surface made of strings. And the Hawking radiation is really just strings radiating from the surface, carrying the information of what fell in. This is the frontier. These are not settled questions. The most brilliant people in physics are working on them, using tools from quantum field theory, string theory, loop quantum gravity, holography, information theory, quantum computing, and they are making progress. Slow, hard, uncertain progress. Let us also talk about black holes in the context of everything else we have discussed in previous videos. The Fermi paradox asked, where is everybody? One possibility is that sufficiently advanced civilizations use black holes as power sources. The Penrose process extracts rotational energy. Hawking radiation from small black holes could theoretically be harnessed. A civilization with access to a stellar mass black hole and the technology to harvest its energy would have power outputs difficult to hide. We look for Dyson spheres. We might also look for engineered black hole energy systems. None found. So far, black holes and the multiverse. The Lee Smolin proposal, called cosmological natural selection, suggests that black holes give birth to new universes inside their singularities, with slightly different physical constants, a form of cosmic evolution. Black holes with larger Schwarzschild radii produce more offspring, since more black holes form in universes that are good at making stars. This is a serious, if highly speculative, scientific proposal. Black holes and time travel. The interior of a Kerr black hole contains closed time-like curves, paths through space-time that loop back on themselves, in principle enabling time travel. Whether these are physical, whether they persist when quantum effects are included, is unknown. The Cauchy horizon, where predictability breaks down, is connected to this. And black holes as the ultimate end, after all stellar evolution is complete, after proton decay has dissolved all atomic matter. If protons decay, black holes remain, the last structures, slowly evaporating. Via Hawking radiation, the final light in the universe, not the warm light of stars, but a cold trickle of thermal radiation from the last black holes, growing fainter, colder as the black holes grow smaller and hotter, and Hawking radiation peaks briefly before the final evaporation, and then nothing. What happens at the final moment of evaporation? This is another open question. As the black hole approaches Planck mass, about 22 micrograms, the size of a single bacterium, quantum gravity effects become dominant. The Hawking temperature diverges toward infinity. The evaporation rate increases without limit. And the final moment, the last moments of a black hole that may have been 10 billion solar masses, the last moments happen in a quantum gravity firework that we cannot currently calculate. Does information emerge in this final burst? Is the singularity, whatever it was, finally exposed? Does the black hole leave a stable Planck scale remnant containing all the information of everything that ever fell in? These are open questions. We have come a long way from the lunch at Los Alamos where Fermi asked where everybody is, to the image of M87 that showed us a glowing ring around perfect darkness, from Schwarzschild deriving his solution in the trenches of World War I, to LIGO hearing two black holes merge 3 billion years ago, and detecting the echo in a laser interferometer 4 kilometers long. From Hawking's calculation on a blackboard in Cambridge, to the firewall paradox that threatened the foundations of physics, to ER equals EPR, and the suggestion that space itself is made of entanglement. Black holes are not just extreme objects. They are the universe's way of showing us the limits of our theories. Every time we think we understand them, they reveal a deeper question, a more fundamental uncertainty. They are made from the death of stars, and they end, eventually, by returning that energy to the universe as the faintest of thermal radiation, across timescales that make the current age of the universe look like an eye blink. And in the center, whatever is there, whatever the singularity really is, behind the event horizon, hidden from us, perhaps forever, we do not know. And the not knowing, the fact that there exists a region of our universe to which our theories genuinely do not apply, is perhaps the most extraordinary scientific fact of the 21st century. Not a gap in human knowledge that more data will fill. Not a question of insufficient computing power, but a fundamental limit. A place where our deepest theories, tested to extraordinary precision everywhere else, simply break down, and something else must be true, something we have not yet discovered. Every generation of physicists has looked at the deepest questions and said, we almost have it, we can almost see the final theory. And every generation has found that just beyond what they understood, there was something stranger, something they had not imagined. Black holes suggest strongly that the next discovery, the discovery that resolves the information paradox and explains the singularity and unifies quantum mechanics with gravity, will be stranger than anything we currently imagine. The universe has been consistently more surprising than our best predictions. And at the center of every massive galaxy, including ours, there is an object that embodies this perfectly, a place where our knowledge ends, where the physics runs out, where something else begins. We have photographed the edge of that place. We have heard it ring when it collides. We have measured the orbits of stars around it. We have built theories about what might be inside. And we do not yet know what is there, but we are asking. And we are getting closer. One observation, one calculation, one experiment at a time. That is either the most humbling or the most exciting thing in science, or both simultaneously, which is exactly what the universe always turns out to be,